One, you're live.
All right, and good afternoon, everyone. My name is Cameron Grass. I spoke with you guys last Thursday for your EET course. We'll be going over some more testing commissioning stuff regarding protective relay applications specifically today. Just another quick overview for presenter information and background. Everyone you see up on the screen, it should be associated with the slide deck that Paul will be giving you guys as well. As always, please feel free to reach out to any one of us for any questions or information regarding field work, just client personnel, anything regarding anything really. Please feel free to reach out to any one of us. So just a quick overview, going over some of the stuff we left off with last Thursday. Just very quickly going over the isolation procedures for prepping testing relays specifically. Quick purpose for writing up isolation procedures. They specifically are used to avoid misops, damage to equipment, or risk of injuries to personnel. Removes in-service sections of station, avoiding any form of DC or AC power flow through pieces of equipment that may be placed into or out of service. So in this application specifically, when we're going to test a relay, we need to isolate the relay thoroughly to ensure that while testing, we don't accidentally cause a misoperation of any in-service equipment in the substation itself, as well as avoiding any form of inrush current or voltage sources to any other pieces of control house equipment that other personnel may be working on. Just a quick overview of the sequence of operations. The isolation procedures steps always take place. You always start by isolating your critical outputs. This may be any trips to breakers, circuit switchers, any form of in-service equipment. This is done specifically first to avoid the relay assuming that a loss of current or voltage source may cause a misoperation. Any other outputs, this could include alarms coming from the relay as well. Those will be isolated next. Communication-based tripping, this may be direct transfer trip, any other POTT schemes, stuff like that. Any inputs coming into the relay will be isolated next, and then to follow up, your currents and voltages will come last. So getting into the relay testing portion of this presentation, just a quick overview before we get into the ins and outs of it. I just wanted to bring up the foundational HPI tools. This is more of an overview specifically for any type of field work or substation work that you guys may be doing in the future. Just some of the key points here that I want to really go over to highlight. HPI, for instance, is human performance impact, and the tools that we use to provide the most safe measures to test and commission any new or upgraded equipment. Stuff regarding, for instance, this first bullet point here, pre-job briefing. Pre-job briefing is pretty much just an overview of the work that's going to be accomplished during the day. This is always done prior to starting any work, usually first thing in the morning when you show up on site with all crew and other personnel that may be either just working or even just walking around the site. Everybody needs to go over everything that anyone would be doing to avoid any conflicts of interest or possible risk of injuries if someone's somewhere where they're not supposed to be during the day. A couple other things, questioning attitude is a big one here. This is really important, especially for new personnel that may not have a ton of field experience. They're usually the best companion to have on a day's work at a site, because although they may not have the necessary information that you have from previous experience on different jobs or just years of testing commissioning experience, but they're usually the ones who will drive the questions of why we do stuff a certain way or certain steps and procedures that need to take place. It's extremely important that we always have a questioning attitude ourselves to ensure that, are we doing this the correct way? Is there a way that may be more efficient or even a safer way to go about testing commissioning? Other stuff that may be classified as a HPI tool would be putting up barricades around in-service equipment to avoid manipulating any switches or touching any equipment that may cause a misoperation. Effective communications, talking with your peers. Always, another one that's really important is our acronym STAR, which stands for Stop, Think, Act, and Review. This applies when there could be a near miss, and a near miss would be defined as something that occurred with no damage to equipment or personnel, but it was caught prior to that occurrence. So you always want to stop, think about what you did, act on it, make any changes that are necessary, and then review to ensure that next time you guys are prepared and whatnot. Next slide, again, just going into the safety measures. Before testing any piece of equipment, whether it be relays, high voltage equipment such as breakers, switches, et cetera, you always want to make sure that you have your personal protective equipment, PPE, stuff like safety glasses, FR clothing, EH-rated boots, EH-rated gloves if need be, and hard hats are all essential when working on a site. Again, just more safety measures to ensure that everyone goes home the way they showed up at work that morning. So everyone wants to go home safe. So what are we going to be testing? So the first steps when we get into the relay testing portion of a project would be to identify the elements that we're going to be measuring, verifying correct operations, any standards or calculations that may have been done by the system protection engineer prior to issuing the settings, all kinds of stuff like that. So quick overview of each of the elements that we're going to be verifying. Firstly, you always start with a metering test on the relays to verify the phasing and the amplitude of the currents and voltages going into the relay. This is done to verify the correct ratios are being used not only on the relay side, but that it matches up with the design side, whether that be on the prints or even on the equipment itself. Different elements such as timers, torque controllers, any blocks associated with each element, these will be tested usually with pickup values regarding current measurements that have been calculated by the system protection engineer. And our job is to verify that the relay correctly identifies these elements and operates when need be. Any inputs and outputs associated with the relay, usually this will be any trip outputs, alarms, incoming DC signals from other pieces of equipment like other relays or lockouts specifically. We're going to be functionally testing all those by applying voltages and currents to correctly identify that they will operate when need be per design intent. As well as protection logic, kind of the same idea, providing injection current and voltages to correctly identify the relay is going to operate when need be based on the protection logic, and as well as displays such as the LEDs, push buttons, all correctly labeled and function as intended. So preparing to test, things to consider, especially with an in-service relay, is identifying. So say we start with an in-service relay, we've correctly isolated it, are 100% sure that the relay will not misoperate when testing, nothing's connected to it. It's literally just the relay and its DC source for power. So if it is a previously in-service relay, the first thing you always want to do when you hook up to the relay is read the as found settings. This is extremely, extremely important, not only to you, but to the client, to correctly identify that you have record of the previously in-service settings. Take any event reports. Again, this is the same idea. It's just another step to cover your ass when you're out there and identify that anything that may happen either during or after testing would not be put directly on you per se, and that you can identify it with the event reports, as well as the SER data and the history as well. So all these steps are extremely important to get like a baseline set of data for record, and also to compare settings later on, which we'll go over. So is the relay prepared? Did the new settings change any LED designations, push button functionality, stuff like that? So if you are testing a previously in service relay and you get a new form of issued settings, they may not line up directly with the push button and LEDs from the previous settings. So you must identify, is there any changes? Are the LED and push button labels the same? Does stuff change? And if stuff did change, do you need to get a new template for the labels? In which case, do you know where the labels are? Easiest way to go about if you do need to change the labels would just be going onto the SEL website, going to the specific type of relay that you're going to be testing, and downloading a either Word document or PDF file of the label templates. And you can edit them from there, print them off. Usually the relays will be delivered, and the client may have extra templates on site for the specific material they use to put into the relay front panel itself, and then you can print those off and replace them if need be. Preparing to test and your connection setup. So again, after isolation, usually you'll identify the points of where you need to hook up your test set to. Going back to what we discussed last Thursday, those knife switches associated with the relays usually are the easiest source. The first step you want to do is correctly identify that each point of the test switch correctly lines up with the port on the relay. And once that's identified, you can usually hook up a paddle or alligator clips if need be from the test set to the knife switches. The biggest thing you want to look out for is verifying polarity on the test switches themselves, that you're going to be injecting currents and voltages to the relay itself and not back out to the yard. This could cause a backfeed of sorts going back up into any high voltage equipment and causing very, very dangerous issues. So once you've identified that all your test connections are correct going up to the relay itself, make sure you have all your correct tools for the job, insulated screwdrivers and your meter. These are all important tools when testing, not just relays, but wiring checks and functional checks as well. Verifying correct test leads, especially when you're hooking up with your meter. This picture shown on the very right is a standard fluke lead. The top black lead is actually much more dangerous than the bottom red lead. And the reason is this metal piece on the black test lead shows much more surface area, which when you're measuring live voltages, especially DC or AC, it could cause a short from one terminal block to the next, or even a short if your finger's close enough to it, straight from you to ground, which will cause either injury or even worse. So correctly identifying the leads are insulated, secured, and properly handled is extremely important when testing live voltages. Again, going over some of the different types of test equipment when you're setting up. This is an older test paddle, one of these States paddles that plug directly into the knife switches. This back piece right here is where it will be inserted, and the front panel is where you'll be connecting your test leads straight from the test set. It's extremely convenient compared to alligator clips, which again can cause shorts between circuits, and that's not only dangerous, but can also damage the relay itself, which will be a big no-no to the client. So if you are using alligator clips, make sure that they are insulated and properly separated from each contact point. As well as when you're connecting to the relay, some of the spare outputs, that you may be utilizing for the testing purposes may not be connected to the knife switches, in which case you'll just be going directly to the back of the relay and screwing in some of these spade connections to directly to the back of the relay for testing purposes. Color coding, I think, is a big deal as well. It helps when you're relay testing. You may be plugging in quite a few leads and test terminals. So being able to quickly identify what lead is going where and what purpose it's serving is extremely important. For example, when I was out in the field doing relay testing, I would use a red, white, blue system for A, B, and C phases. I would use those both for the currents and voltages and make sure that they're separated well enough to correctly identify which one's the current, which one's a voltage. But just something like that to make good practice when you're testing relays off and on. Barriers as well. Again, going back to the fact that sometimes stuff happens. You may go out to lunch, may not remember specifically where you left off testing, but making sure you're correctly identifying the piece of equipment that you are going to be testing and you don't move from that point is extremely important. So stuff like tags, just any type of barricade, whether it's just a big old slab of paper across any in-service equipment that you know you shouldn't be touching, tape surrounding the relay that you will be testing, stuff like that is extremely helpful. And just another piece of advice for you. So looking at, this is a Doble F6150. This is a pretty standard piece of equipment for relay testing, especially on the new SELs, any GE relays as well. It's common for new equipment to be tested using this 6150 because it's not only compact and easy to use, but the software itself is fairly straightforward for the most part after a couple test runs. So the identifiers here,
He's
we'll
saying
just go
that
right
very
down.
kindly. It's not the easiest software to use. So it's
No,
more than a couple test runs. I've played with it. I'd say a little more than one or two. So
yeah, it might be more, Paul. You're right. Yep. What I will say, Paul, is the identifiers for the front panel itself, maybe not necessarily software. The software gets a little more in depth, but the identifiers on the front panel of the test set are mostly straightforward, but we'll just go through these fairly quickly. So in the blue square here, you have your current outputs, and in the red square, you have your voltage outputs. Now, one tricky thing about this is when you are opening up the software, you can actually flop these ports, change them from AC current to AC voltage on one side and AC current and AC voltage to the other side. So making sure that you identify these before you start injecting any currents or voltages is extremely important as well, because you don't want to be putting currents into the voltage sections on the relay. So your logic terminals here shown in the green and yellow squares are going to be your outputs and inputs. The outputs are for the test set specifically. So this will usually be connected to the battery simulator here in this purple square, which is a DC source that you can enable from the test set or from the software itself. This will usually be 125, which is standard for most of the relays that you'll be encountering. This DC source will be plugged into your logic outputs if need be, which will, these are usually normally open contacts when applied to DC voltage source on the top side. You'll connect the bottom side to any inputs going into the relay, and then you'll have your return back to the negative side. So this will stay open until you construct a test for this to close when needed and verify operation on the relay pickup. Your input side is actually used for the output side of the relay. So if a relay has an output that you're trying to test, you usually plug the low side of that into the high side of this input side and plug the low side back into the reference. The black square over here is all your communication terminals. This will be utilized when you're doing any goose testing, end-to-end testing, stuff like that. And I will be quickly going over some end-to-end testing Thursday, so we'll get into the good stuff of that later. All right, going back to a point I made earlier, verifying your analog connections from your test set directly to the relay. So as shown here, we can identify that this 21L B2 is the relay we're going to be testing. As shown in the 3-line schematics, your voltage and current sources coming into the relay is correctly identified. There would be more of a section for this voltage class going back to the PTs to verify ratios and phasing as well, as shown as the current here. So configuring the test switches, making sure that you correctly identify the phases per the inputs to the relay. So you want to identify and verify that phase A from the PT source is going into the phase A port on the relay. Same for B and C, and making sure you have your reference. Same here for your phase A, B, and C currents as well. You want to verify that they're coming off the correct CT. It's going through correctly polarity wise and got your return as well. And like I said as well, verifying your ratios prior to injecting any values would be extremely important for your metering test and going forward for any other additional tests. So this is kind of a rough sketch of what your test leads will look like once plugged in correctly. Starting with the voltage sources, these are usually pretty straightforward to hook up. Once you've correctly isolated your knife switches and there's no other voltage source going into your relay that you're going to be testing, you'll just directly plug in your A, B, and C phase voltages straight into the relay, making sure you also have your reference back to ground. The currents get a little bit trickier, however, mostly because the way current works, obviously, is it's a flow state. You need to verify that the relay is going to be receiving and the correct current values. So in this case, you'll have your phase A coming in, and you need to jump. Usually, once these are isolated, you'll need to jump 7, 11, and 15 altogether to get your reference back. Otherwise, it's an open CT, and the test set won't even allow you to inject any current. So stuff like that is fairly tricky until you get the hang of it, and then once you do, it becomes pretty self-explanatory. So just again, quick overview: phase A, B, and C going in, making sure all 3 phases are jumpered back to a reference to verify that each phase is correctly connected. So let's see, analog connections. I believe, so this is the same idea. Verifying polarity is extremely important. As I said before, in this case scenario, say this set of test switches here, A, B, C, and J, are actually flopped. So you're isolating from the PT side. When you go to plug that in, if you didn't correctly identify that the point of contact from your test set is not going directly to the relay and maybe going elsewhere, that can lead to, again, backfeeding to high voltage equipment, which can cause extreme issues. It can also go elsewhere to other pieces of equipment, again, in-service relays that may be connected in parallel, cause misoperations, just more and more damage and more issues. So as long as you can confidently identify that where you plug in your current and voltage injections is directly correlated only to the relay that you're going to be testing, then you should be all set. So connecting spare output, this is a common practice for testing because it's extremely easy to manipulate a spare output that's not going to be utilized. Usually, again, by doing this, you'll connect directly to the back of the relay, because if it's a spare output, it won't have anything connected to it to begin with. The spare output contact is used for manipulating elements, testing them, and verifying them. It's easy to use because it's not going to be utilized for any other function other than what you're going to be implementing yourself. It's also going to be polarity sensitive sometimes, so you'll want to watch out for that and make sure that you got it all set up. And yeah, like I said, it sometimes as well, these spare outputs can actually go to a knife blade and nothing else. It'll just go down to the knife blade and can be even easier to connect to rather than going to the back of the relay cabinet. Instruction manual. This, if you're getting into relay testing, the first thing they're going to tell you if you have any questions is, did you look at the manual? Because pretty much 99 times out of 100, you'll probably find your answer in the relay manual. It's a lot easier said than done because these relay manuals will be anywhere from like 600 to 1,000 pages of just everything to do with whatever relay you're testing. But there's lots of really, really useful information in the manuals that can not only help you during the specific tests that you may be running, but for future testing purposes as well. Reference documents is just extremely helpful in the field. So yeah, it's especially when it's digital, you can use a Control F to search any elements that you may be testing, commands, relay word bits, stuff like that. It's extremely useful. So what are the limits of the relay? This is something that you should identify prior to starting any injection values, or even if it's a relay that's completely isolated, even from its DC source, identifying what the DC rating is for the relay. Because as I said before, that battery simulator terminal on your test set can be manipulated anywhere from, I believe, 0 to 250 volts DC. So you want to correctly identify that you're implementing the correct DC voltage to the relay so you don't burn that out. So you also, going on the AC side, you want to look at the relay manual and the specifications to identify what the max current ratings, voltage ratings, pickup ranges may be prior to setting up your test plan or injecting any values. You want to determine the accuracy range for testing purposes as well. Does the relay act differently at different ranges? This could be extremely important, especially for time over current elements. And other examples such as thermal ratings, saturation currents, continuous thermal ratings, et cetera, et cetera. A lot of this information seems like it would be redundant, especially after you test a bunch of relays, but especially nowadays where there's so many different types and versions and standards that clients may use, it's fairly important to identify that you not only have the correct relay manual, but you identify the limits of that relay specifically. Going back to your test prep, the SER stands for Sequential Event Recorder. This is data that may be associated with any elements that you may be testing, stuff that may show up. It's pretty much an event recorder of sorts for testing purposes and also in service purposes as well. So for testing purposes, the SER is extremely important to use for proving elements pickup when need be. This can be done usually during state simulation tests, where you'll be identifying an element that you want to show pickup, and you don't have a way of doing it through the software itself. You can implement any current voltage ratings, a dropout, have a contact open or close when need be, and record all that data through the SER. And the client likes seeing this data as well because it's time-stamped, dated, and shows every contact or element that picked up or dropped out during the test. So it's, again, another piece of data to show as a reference, but also cover your ass when stuff may happen in the future. You have something to show to prove that you did it correctly. Reviewing the DC schematics, identifying the outputs specifically. What outputs are they going to be monitored? What ties to the other relays? Verifying your isolation points and pulsing and measuring contacts. So during testing, you'll want to identify the correct operation of each output and verify that it picks up properly. So for example, here on this out 201, it's going to be tripping TC1 on your breaker BL2. If there's any if there's any protection logic associated with that output contact, you'll usually run that test first, identify that it works as design intent, and then later identify that the output closes when that protection logic goes through. So correctly setting up your test points from the output side of the relay to the input side of your test set is important as well, because that way the software identifies that the output did in fact pick up when need be, especially when you're getting into such finicky tests where you're verifying operations at like nanoseconds. So yeah, it's very important to identify those to begin with. Going into it a little bit further, monitoring your programmed outputs, the points that it may contact, and your local isolation point. Again, if these outputs aren't associated with a knife blade, as shown here on this BFI and RI, which stands for the breaker failure initiate and reclose initiate, you'll want to identify that these output contacts are isolated elsewhere and that there's no other way for this output to trigger an event. And then most likely what you'll need to do is either go to the back of the relay cabinet and either hook up to the terminal blocks associated here with this 2 TC4 and 3, or just go straight to the relay and go to Bravo 3 and Bravo 4. Usually you just pick the point that it's easier to access. So reviewing DC schematic inputs. So on the input side of the relay, you want to identify what inputs are programmed in the logic, cause the input to go either high or low, and what are the limits, especially with the open and close of a breaker and tripping lockouts. Again, identifying your isolation points, correctly hooking up your inputs on the relay side to your output side of the test set when testing is extremely important. Some of the dangers here, especially identifying the operation of your BL2 breaker. This 52A contact determines whether the breaker is either open or closed, and you need to correctly identify that to the input of the relay. So going a little more in depth into that, this 52A is associated directly from the breaker itself, identifying whether it's open or closed. So if the polarity on this is opposite of what the relay is seeing, that could cause immense issues, especially when you go to restore the relay and put it back into service. Because if the breaker is closed, but the relay thinks it's open, then the protection is not going to be enabled because there's nothing to worry about. The breaker's open. Whereas if a fault were to occur and the relay doesn't identify that the breaker is in fact closed and that there is a fault, nothing will happen, and the breaker and other equipment could be immensely damaged. As well as the other side of it, if the breaker's closed, if the breaker's open and your relay thinks that the breaker is closed, it can cause misoperations such as reclosing, triggering open and close functions on the breaker multiple times over, which can again cause damage to the equipment itself. And also, if there is any other form of communication tripping, whether it's to another site or just to a different piece of equipment in the yard, that can open up as well, which can cause loss of power to customers, which the client does not like. Going into some of the other stuff, this breaker fail transfer trip. Again, this is associated with a breaker failure situation where a fault can occur in the site and pretty much need to isolate more than one piece of equipment to ensure protection to the in-service stuff. This will be done usually over a POTT or direct transfer trip if it's communication based, but in this case, it's actually just coming from a lockout. Relay test mode as well, if the relay utilizes it. I don't see this necessarily too much in my limited experience, but again, if it is there, just correctly identify it and make sure it works properly. So I actually have a lot more that I'd like to save for Thursday. So in this case, let's see, what else can I go over this? I do have another slide deck, Paul, but I'd like to kind of save the more in-depth stuff for Thursday, just to kind of hit it all in one piece, unless you want me to go over relay testing locally and then save Thursday for any end-to-end testing or communication-based testing. It's up to you.
I'll totally leave that up to you.
Okay.
Whatever you think flows better in terms of the understanding. That's
Sure.
It's just definitely outside my realm. I understand a little bit about it, but I'm definitely not an expert at it.
Yeah, absolutely. Let's see. I guess I can let me open up this other slide deck real quick. I'll go over some of the local relay testing stuff to begin with, and then we can I'll try to put together some more stuff regarding maybe communication-based testing, such as end-to-end for Thursday, and then get into some of the restoration stuff as well. So let's see. All right, so local testing. Pretty much just going to go over configuring your test set and your test plans, identifying the elements that you're going to be testing themselves, and how to create state simulation tests. So we're going to get into the 6150 program utilized with the test set in this presentation as well. So this is a quick little screenshot of what you'd see when you're initially opening up the software. In this instrument tab, you can identify your sources as discussed earlier. You can actually change these from your voltage to currents and flip-flop, et cetera. You can also utilize the underside ports as well for additional voltage or current sources, especially when you're doing end-to-end testing that may include different directional current elements that may be utilized for pickup purposes. Usually, as shown here, it may be a 66.4 voltage source for the AC section. This will change depending on not only the PT ratios that you're going to be utilizing, but as well as what the relay settings basis documents indicate. So you want to correctly identify that all those calculations line up correctly prior to injecting any values or starting any testing, because sometimes you may run into issues such as elements not picking up and you're wondering why, and troubleshooting forever, and then realizing that your source voltages aren't even correct and the relay doesn't even detect it to be properly injected. Getting into the SEL terminal side a little bit, this is an extremely useful tool when testing, because it's a little bit complicated to begin with, but once you understand the commands, it becomes extremely easy to set up SER data, setting outputs, targeting bits when testing, et cetera. So some of the commands here shown are specifically related to the metering stuff. As you can see, there's a lot of metering commands associated that may be used for different purposes. The set command is extremely useful when testing certain elements, going back to what we discussed earlier based on the spare output. This is how you'll utilize that spare output when setting up your test plan. Say you're testing a 51 GP element and you want to associate that to an output so that your test set can understand when it gets picked up. You would be going into the terminal using the set command, identifying the output that you are plugged into, and utilizing the element that you're going to be testing at the end here. The control panel in the 6150 software is also extremely useful for not just your test plans, but any just random voltage or current injections that you may be doing for other test purposes, such as functionals, metering purposes externally, as well as automation testing as well, identifying that if the relay is picking up currents and voltages and sending them to the client's dispatch or HMI screens as well, that you can use this to directly set up your current and voltage leads, set up your amplitude and phases, et cetera, and we'll go into that detail right now. So here on the left in the green square is your analog channel names. Again, this is what you'll be utilizing to identify which phase and which current or voltage source you're going to be using. This blue square here identifies the maximum range that you're going to be outputting. This is usually just a safety measure in case you accidentally mistype a value that you're going to be injecting. If it's too much and the relay can't handle it, you could burn up the contact, or even worse, just shut off the relay completely and trash it. So setting these current and voltage ranges is important for safety measures, as well as ensuring that the equipment is going to be safe if an error were to occur. This purple square over here is going to be your injection values. It goes into the amplitude and phase, and as well as frequencies for your currents and voltages. Again, as we discussed earlier, 66.4 would be your nominal voltage based on the PT ratios as well as the relay settings. Your nominal current ranges can differentiate based on what the relay is going to be looking at, what the settings engineer implemented for the basis, as well as the phase angles for certain testing elements to be picked up and show differentiation on your chart over here. In the orange square over here is going to be identified your inputs and outputs from the test set. So another key important factor is identifying that your inputs and outputs that you're going to be utilizing from your test set have been enabled and identified properly, so that you understand which input goes where and that it's actually going to be picked up when testing. Another couple sections here, this step ramp and pulse settings section is extremely useful for manipulating current or voltage values while the test set is actually running and injecting. So this can be utilized when you start up the test set and begin injecting values into the relay. You can actually set parameters for a step or ramp to be placed, and you can manipulate that while the test set is actually live and change the values in real time, which is extremely useful, especially when you're testing multiple different points and different values. You don't have to keep shutting off the test set and turning back on, et cetera, et cetera. You can just change them here. And you can change not only the amplitude, but you can change the phase angle during testing, as well as the frequency. This section up here, as shown as well, this will actually allow you to enable the step or ramp change to either one or multiple sources during testing, which again is extremely useful if you want to just manipulate one phase at a time or one value at a time. And then the last section, again, before you freak out and wonder why your relay is not getting any voltage or current readings, always check to make sure that your outputs are enabled, and make sure that you allow the current or voltage to be injected into the relay. So the first test you always want to run after you've taken all your necessary recorded data, such as the SCR, event recordings, history of the relay, stuff like that. The first thing you want to do when initially setting up your test is a metering test. This is extremely important because you want to correctly identify that the voltage and current values that you are injecting correctly replicate not only the relay settings ratios, but as well as the ratios that are identified on the field equipment. So for example, before you set up your test sets configurations for the values, you want to identify that the basis and settings information that you receive from the protection engineer correctly matches up with what the ratio is going out to the equipment. Once you've identified that they match up correctly, you then go in, make your calculations, and identify your phases as well, which in this case, usually it's common practice to do a 10, 20, 30 for your voltages at 0, 240, and 120 degrees phase angle, as well as a 1, 2, 3 for your current amplitude. The reason we do different values for each phase is so that when you do look in the relay in real time while you're injecting these values, that you can correctly identify that each phase correlates properly. Because if you put 10 on all 3 phases of your voltages, you're going to look in that relay and it's going to be all the same value. So you're not really verifying that each phase correctly replicates what's being read on the relay. Same goes for the currents as well. So an example here, this is a copy and paste from the metering command from the relay terminal that we were talking about earlier. So the test engineer put in its different phases for different values for each phase for the voltages and currents, correctly identified that the previously calculated ratios match up with what should be seen on the relay. And once that's done, you can confidently verify that your ratios and measurements will be correct going forward when doing the rest of your testing. Going back again, the relay terminal is extremely helpful for setting your outputs when testing. Like I said before, if you hook up a spare output to your test set, you can manipulate that output as many times as you want to during the course of testing without having to log into the relay and change it directly and send new settings back and forth, because that would take forever. This way in the terminal screen, you can actually just change it, press enter, and the relay just takes it and you can go on with your testing and then change it again on the next test. It's pretty convenient and super helpful for getting testing done time efficiently. So setting up your first test plan, as shown here in the software, you start a new test. You have a drop box here of different types of tests that you may be wanting to implement. Some of these tests can be correctly identified based on what element you're going to be testing from the relay settings. Stuff like steady state tests will have linear pickups, testing your zones of protection, your Mo circles, et cetera. State simulation tests as well. That's for testing the relay logic when you can't correctly identify an element you want to pick up, but you're more or less testing the internal logic of the relay, as well as any output or input contacts that you may be wanting to prove as well. So quickly, just kind of not gonna go too deep into this. I'll save that for Paul's relay course, but just kind of a overview of some of the different types of tests. For example, this first one here, a 51G. So what we're looking for here is the residual ground instantaneous overcurrent element that the relay is identified and going to be utilized in its protection. This will be done by identifying the pickup current, testing the zero sequence, and utilizing a ramp test as previously shown in this slide, which would be under one of the steady state tests. So setting up your test parameters, excuse me, we'll go right into it. Actually, it shows in this next slide. So identifying the tests that you're going to be running, for this 50 G1. In this case, we're going to be using linear ramp current, and this will bring you into your settings pretty much. So shown here up in this top left corner in the blue box is going to be your expected test point. Now, as shown in the previous slide, your expected test point for this 51G element is going to be 3.87. This is what you'd be utilizing here. This is what the test set should be reading when you're testing the element, and it will be shown in your results as well. Your test parameters are usually identified, again, utilizing the relay manual is extremely important because it will inform you of what the parameters should be for your offset current, any limits that may be needed on the relay itself, et cetera, basically all the relay specs that you should be identifying before starting your test. In the red box over here, you got your analog inputs. This will be all your voltage and current values that you're going to be implementing. Usually you will be using your nominal voltage and currents other than your action current, which we'll go over later. This sense setting is where we'll be utilizing the test set's input. So basically what we'll be doing is running this test. Your sense connection is actually going to be connected to that spare output that we're going to be utilizing from earlier, setting the spare output to the 50G1 element, and that's what will be utilized when you're running your tests. It's going to close that output and cause that input to pick up on your test set, and that's what it'll be sensing. As well as your unit info down here, this is basically determining whether this is going to be primary or secondary values that you're going to be injecting, as well as what the time values would be, whether that's in cycles or seconds. So as shown here, you can see that the test engineer filled in all the parameters that were what would be necessary. It's got the 3.87 amps for the expected test point. Got your offset currents, offset durations, and your current limit, which would usually just be a little bit above your expected value, as the relay should be expected to detect values down to the lowest decimal you can imagine. As well as a sense connection. Again, we're utilizing this out 213, which was a spare contact, but we're actually manipulating it to be a 50G1 pickup contact. So when that element picks up during your test, output closes, the test set detects it and stops the test. So setting up your expected results, this will be, excuse me. Down in this lower box here is going to be what your results bar will look like. It will show you your value for your expected results, the measured results after the test is complete, and the tolerance here is for your sake, especially once you get into more finicky elements. You can actually place a buffer in there if it's not supposed to pick up on the specific value. You can give it somewhat of a buffer, especially when you're getting into, you know, crazy small current values and stuff like that. And then as shown here, you can see that the results were actually perfect. Your expected result was supposed to be 2.32 amps. The relay picked up the contact at 2.32 amps when running the tests. And in fact, there was actually not even a tolerance that was needed, which is always nice. So creating a state simulation is, again, extremely important when you're testing the protection logic in the relays. The state simulation actually looks somewhat similar to your control panel. You set all your parameters, such as your voltage readings, current readings, the maximum duration of the cycles, and any outputs that may be manipulated during the test. So in this case, we'll be, let's let's say we're testing just a simple output contact from the relay. Usually, say it's a trip contact, and you want to correctly identify that the correct output contact from the relay is picking up when need be. You'll set up your nominal values here, set up a set of fault values in your second state, and then return them back to nominal to indicate that the test is done. During this section where there is a fault state is also where you want to put in your sensing contacts, because when you initiate a fault on a trip contact, you want the correct output contact to pick up when need be. Your test set will identify that and then return the nominal and currents, return the nominal voltages and currents back to where they were. So setting up an alarm input. In this case here, we're actually going to be utilizing the output contacts from your test set going back into the relay. In this case here, you can see the test set is going to be connected from any high side current voltage source for the DC side, going directly to the top side of the input that you're going to be testing. And as long as you have a return path on the other side of your input, then you can complete the circuit and verify that the correct input picks up. You can also see that if there's other logic that may be going into that input, such as a push button, a switch that may be associated with it, any other contacts from other relays or a piece of equipment, that you utilize those as well and indicate that the input from the relay picks up when necessary. Proving your logic. We're looking at monitoring the output contact from the test set again. So this is a sense state for pretty much when you're running your test from the state simulation, that you pick up and drop out the output from your test set to the relay when need be. This is extremely helpful when testing stuff to verify that the relay operates when it needs to and not when it doesn't need to. And what I mean by that is, say you have a piece of logic as shown here, say this this push button 1 and PLT indicator is associated in this input logic. You want to correctly identify that the relay picks up when both these pieces of logic are true, and not when one is not and one is true, and vice versa, and et cetera, et cetera. So this is extremely useful for allowing the test set to not only initiate the correct output contact when need be, but also the relay doesn't pick up when it doesn't need to. Proven logic, let's see here. Let's see. Yeah, I'm just going to highlight this one last little section here, and it's going to be timer values that may be associated with the testing as well. So the timers are extremely useful for the state simulation tests because it can indicate when an element needs to be picked up, especially if there's a delay in the logic, because you don't want the relay to initiate a trip based on an instantaneous reading, especially if there's supposed to be a delay in it. Especially common practice, especially for reclose initiates. If a breaker opens from a fault, it has a delay in there for nominal voltages and currents to return to the relay before initiating another close back into the equipment. The timer section for this setup is pretty handy when utilizing all those state sims. So this end-to-end testing I'm going to save for Thursday, as well as I'm going to go through just a quick overview of the restoration procedures that we use when we're placing a relay and other equipment back into service, going over some of the types of readings that we'll be taking, for example, from the relays, physical measurements utilizing a phase angle meter to correctly identify amplitudes and phases as well. So I know that was a lot, and I'm sorry to kind of go over this so quickly, but if you guys have any questions, I'd be happy to answer them to the best of my abilities.
Can those testing devices input like a small amount of fault current?
Yep, absolutely. That's that's usually what you'll be doing for your state sims. So when you're setting up your fault current values, usually you'll, like, say you want to do an A to ground fault. In that case, you'll have your nominal voltages and nominal currents for your first state. Your second state, if you're going to be doing an A to ground fault, you'll put something, again, within the relay, the relay's parameters, something, let's say, for example, 10 amps on phase A and 0.1 on phase B and C, as well as a very low voltage value, such as 5 to 10 volts on phase A, and either a nominal or a little bit higher voltages on phase B and C. With those magnitudes going into the relay, that relay indicates that there is an A to ground fault occurring based on the extremely low voltage readings on phase A and the extremely high readings on phase A currents. So that's a really common practice when detecting fault pickups when relay testing. So
Yeah, and if I could just add,
Sure,
remember,
please, Paul.
these are secondary currents, not primary
Correct.
currents. So a fault current on the secondary side could look like 2 amps, but that could be 75,000 amps when you factor in the CT ratios. So all those values that they're injecting, you see the 1 amps, that actually could be equivalent to a fault on the high side, but the relay can't tell. That's just a secondary. So keep in mind the secondary has a nominal rating to 5 amps. And anything beyond that would be considered, typically a fault condition, but not necessarily. Like on the ground, you typically set it much more sensitively. So having 1 amp for ground is a pretty common one. And you may or may not need the low voltage. It just depends on how you polarize the elements.
Yep. Anyone else? Any other questions? Maybe some stuff that I kind of breezed over that you kind of want to get into a little deeper, or anything?
Okay, well,
Sweet.
we're ahead of schedule. Thank you so much for the presentation, Cameron.
Yeah, my
And we'll
pleasure,
see
Paul.
Cameron on Thursday for our last class for the semester. Thanks,
Yeah, it's your
everyone.
guys' last class. Nice, awesome. Cool.
Yeah.
Perfect. All right. Well, thank you guys for your time. I appreciate it.
Thanks, everyone.
Thanks, Cam.
Thank you.